This is Word2G. It is an online multiplayer game playable in a browser and was made in 48 hours for the Mixing Game Jam 2020. Basically, when you join the game, you're given a random chess piece and a hidden word. The point of the game is to guess other players' hidden words while trying to hide your own. Every 10 seconds, everyone moves simultaneously, and if your hidden word contains any of the 4 letters on the tile you land on, everyone will be able to see those letters. When you guess someone's word, you'll get a point, and they'll be given a new chess piece and hidden word. But that's not why you're here. You want to know how to make an online multiplayer game quickly and easily. As a solo indie developer, the most important thing when making multiplayer games is cost. I know a lot of people aren't going to be playing my games, so I don't want to pay for servers when people aren't using them. That's why for this project, I'll be using a couple AWS services to go with a serverless approach. This way, I'm only paying for server time when it's being used. If no one is playing the game, I'm not paying anything. AWS also has some very generous free usage that we'll be utilizing. After the game jam, my final bill for the month was about 6 cents. For those of you who don't know what serverless means or have never used AWS before, here's a quick rundown. Amazon got pretty huge and needed servers all over the world to host their website. Once they set up all these servers, they were like, hey, we've got a bunch of computers all over the world that we aren't using all the time. We should sell access to these computers to people to do whatever they want when we're not using them. So they released a service called EC2. EC2 basically means you can pay Amazon to give you access to one of their many computers around the world. You can connect to them with a remote desktop app and use them the same way you would use any computer. While that's nice, a lot of people are like, hey Amazon, this EC2 thing is great, but I don't want to pay for this computer 24/7 when it's not doing anything most of the time. Can I only pay for the amount of time I use it for? And Amazon said, sure, just write some code and we'll run it on our computers for you and only charge you for how long your code runs. That service is called Lambda and it'll be the basis for our serverless design. Amazon has many services, but for our purposes, we only need to worry about 3 or 4 of them. Here's a general flowchart of how the game works. Over here are the players. Each player is using their browser to run the Unity game. As an example, let's say player 0 wants to guess the player 1's word is the word secret. The player will type that in and hit enter. Unity will then create a JSON object which has a field called action, which in this case is the word guess, as well as the word the player is guessing. Unity will then pass this JSON object to the small JavaScript file, which will send the packet through a WebSocket over to our API gateway endpoint. API Gateway is a simple AWS service that just looks at the received packet, reads the action property, and sends it to the corresponding Lambda function. In this case, action says guess, so API Gateway will route it over to our guess Lambda function. The Lambdas are where all of our server code lives. The last AWS service on this chart is DynamoDB. DynamoDB is a serverless key value database. You can create tables and add entries to those tables to store the state of your game. Think of each table like a hash map where you give it a key and a value to store to that key. For this example, we have a DynamoDB table called Players, where the key is the API Gateway WebSocket connection ID, and the value is all the data we need to know about them, like their current position on the board, their hidden word, etc. For this example, we first query our Players DynamoDB table to get the data for all the players currently in the game. The response from DynamoDB will look something like this. Our Lambda then goes over this list of players and sees if any of the words match the guessed word. Since that is the case, the Lambda then updates player 0's DynamoDB entry to add 1 to their score, and updates player 1's entry to give them a new word and piece. The Lambda then sends a packet back to all the connected players that looks something like this. This packet will tell the players' games what to do and contains information like whose word was just guessed, what the word was, and what their new piece and position are. And that's pretty much the basics of how this design works. The players send packets to API Gateway saying what they want to do in the game. API Gateway runs the appropriate Lambda function. Lambda queries and updates DynamoDB tables and then sends updates back to the players. While this approach to online multiplayer is great for turn-based games, it does not work well for games that need to be constantly making updates. For example, in a first-person shooter game, you'd want to be constantly updating and sending player positions to all players. That increases the amount of calls you need to make to DynamoDB by a lot, and at that point it makes more sense to use a server approach so you can cache those values locally on your server instead of in DynamoDB. Also, this design doesn't work well for physics-based games. Since the logic needs to be written in the Lambda functions, you can't just use a headless game client to simulate the same physics your players are seeing. However, I highly recommend this serverless approach for any games that don't require a lot of back and forth between client and server. Things like classic turn-based board games, simultaneous turn-based, card games, things like that. So with all that information, let's get started going over the nitty-gritty of how to actually implement all this stuff. To demonstrate the full end-to-end of how to make an online multiplayer game, we'll be putting together a simple game where players can click anywhere on the screen to move their player token to that location. The first thing you'll need to do is create a new AWS account. Head over to console.aws.amazon.com and click Create a new AWS account. Some of the free tier usage is only applicable to the first 12 months after creating a new account, so I recommend creating a new account for each game you make. You can use the same email address for all your accounts, just add a plus followed by the name of the game before the @ symbol. Then, once you log in, you'll see something like this. You can select the services dropdown in the top left to see all the services AWS offers. If you ever want to check what you'll be billed for the month, select billing. The first thing you need to know about AWS is that pretty much all the services are regionalized, meaning that when you create a resource like an API Gateway API, Lambda function, or DynamoDB table, it is specific to a certain region. In the top right of the console page, you can see a region dropdown. Select whichever region you want to host your game in. Keep in mind that you'll want to keep it as close as possible to where you imagine the majority of your player base will be. Whenever you're using the AWS console, make sure you always have that region selected or you won't be able to find your resources. You also want to make sure all your resources are in the same region or you'll be adding unnecessary latency when making calls between them. Alright, so the first service we want to set up for our game is API Gateway. Open the API Gateway console page and select WebSocket API. Next, name your API the same name as your game and click Create Blank API. Scroll down to the bottom of the next page and hit Create. This page is where you'll be setting up which action properties route to which Lambda functions. There are 3 special routes available as well. Those 3 routes are for when a new player connects to the WebSocket, disconnects, and a default route for when the action property they give you doesn't correspond to any other routes you set up. Now that we've got our API created, we need to create Lambda functions for our API to route to. The first Lambda we want to create will be called join. This is the function that we'll use after a player connects to the WebSocket so that we can add them to the players table. The reason we're making a join route instead of using the connect route is because you cannot send messages back to the player until the connect Lambda is finished executing. After a player joins, we want to send them back information about the game they just joined, but since you cannot send back information during the connect route, it won't work for us. So, open the Lambda console page and click Create Function, then set the function name to join. Click Create Function. We'll be using Node.js as our language for our Lambda code, but you can try other languages if you'd prefer. I recommend Node.js if you can though, because I believe it has the fastest cold start of any of the available languages. If you don't know what a cold start is, basically the first time you run a Lambda function, it needs to be loaded onto one of Amazon's computers, so it takes a bit longer to run. If a Lambda function has been run recently, then it will already be available on a computer and will therefore run faster. From this page, you can edit your Lambda function in browser. Here's a basic outline of how this function will work. First off, I always like to include a comment at the top of all my Lambda functions that shows what the expected input and output of the function are. This helps me keep track of what a function does. Next, I like to outline all the steps my Lambda will take with to-do comments before I actually start implementation. As of now, this code will simply log the input it's getting and then return a packet with property test and value test. This is so we can confirm it's working later. Copy this code to your own join Lambda or grab it from a link in the description and hit deploy to save changes. After you run your function and make some logs, they'll be available in the CloudWatch console page under log groups. Next, we need to make the join route in API Gateway. Open up the routes page for your API Gateway API and type join into the box that says new route key and hit the check mark. In the box labeled Lambda function, type join and check the use default timeout box. After you save, also hit the add integration response button in the top right. This means that whatever we return from the Lambda function will automatically be sent back through the WebSocket to the player that made the call. Go up to the Actions dropdown in the top left of the Routes page and select Deploy API. Select the production deployment stage and hit Deploy. Select your production stage and note the WebSocket URL at the top of the page. This is the endpoint that your players will be connecting to. If you've set up everything correctly, that means your game's API has been deployed and will invoke your join Lambda if someone connects to your WebSocket URL and sends a join packet. Let's test that by starting up Unity and start making the game client. Open up a new Unity project and create a game manager script. The first thing we need to do is add the Newtonsoft JSON package to our project. We will be using Newtonsoft to turn C# classes into JSON objects and vice versa. To do that, open Visual Studio and click Project, then Manage NuGet Packages. Then click the Browse tab, and it's usually the first one called Newtonsoft.json. If not, search for it. Click Install. Next, we need to move the NetStandard 2.0 DLLs into our plugins folder. To do that, open your projects folder and go to Packages, Newton.json, whatever version, lib, NetStandard 2.0, and copy both those files. Then go back to your project folder, open Assets, and create a new folder called Plugins. Paste those files in there. The next step is to change your Unity build options and player options to build to WebGL correctly. Open Unity and select File, Build Settings. Select WebGL, check the Development Build box, and click Switch Platform. Then hit Player Settings and scroll down to API Compatibility Level and select .NET Standard 2.0 if it isn't already selected. The final setup step is to include what's called a link.xml file in your Assets folder. When building, Unity will sometimes try to get rid of files it thinks it doesn't need after compilation. By typing these lines into link.xml and adding it to the assets folder, we can tell Unity to keep those files instead of throwing them out. In order for Newtonsoft to work correctly in WebGL, we need Unity to not get rid of this light lambda file. You can find a copy of the link.xml in the description. Alright, so there are two more files you'll need to grab from the description. Websocket.jslib is the small JavaScript file I was talking about during the flowchart section that allows Unity to communicate with the browser and send and receive data from the WebSocket. Copy websocket.jslib and put it in your assets/plugins folder. Open it up and replace the WebSocket URL with your API Gateway production endpoint. This file consists of two functions, WebSocket.init and WebSocket.send. We can call these two functions from Unity. Inside WebSocket.init, we also set up two callbacks for when the socket receives messages and when it is opened. These callbacks will run the methods called receive and init on a game object in Unity called networking that we'll also have to make. The second file you'll need to hippity-hoppity over to your project is Websocket.cs. This is the C# script that will be calling those two functions in Websocket.jslib and listening for the callbacks. So first, create a new game object in your scene and call it networking. This name has to match what is in Websocket.jslib. Then attach the Websocket.cs script component. Once again, replace the WebSocket URL in this file with your own. Okay, this script is going to look a bit intimidating, but that's because it has a re-implementation of the Websocket.jslib but in C# for when you're running the game in the Unity editor instead of in browser. If you take out that section, the code is actually pretty simple. The most important part of this file is the receive method, which is where we'll be turning the JSON objects we get from the WebSocket into C# classes and then notifying events that our game manager will be listening to. Oh yeah, you'll also need a packet class and packet action enum as well. They're pretty small, but go ahead and grab those from the description as well. So what we want to test is that Unity can 1. Connect to our API Gateway WebSocket, 2. Send a packet that has an action property with value join, and 3. Receive back a packet that has a field test with value test. First, let's create another game object, call it manager, and attach the game manager script. In the game manager script, let's listen for the init event coming from WebSocket that tells us that the WebSocket is connected. Once that event fires, have the game manager send a packet with action join through the WebSocket. That should be good enough to test that our API gateway is working. Let's test. And yes, it works. We sent a join packet and got back a response from our Lambda. Now that we've proven we can call our API gateway and join Lambda from our client, let's go back to Lambda and actually implement our join function. Looking over the list of to-dos, it looks like we'll need to create a players table to keep track of connection IDs and positions, so let's go ahead and create that table now. Open up the DynamoDB console page and click Create Table. Set the table name to Players and the primary key to connection ID. Next, uncheck Use Default Settings and also uncheck Read and Write Capacity Autoscaling. It says the estimated cost is going to be $2.91 per month, but that'll actually be free since DynamoDB free tier actually allows for up to 25 provisioned read and write units per month. Click Create. The connection ID is the unique identifier for the WebSocket connection the player made with our API Gateway API when they connected. That connection ID is always provided in the event data sent to Lambda. Now that we've created our players table, let's get back to implementing our join function. In order to call other AWS services from our Lambda, the first thing we need to do is import the AWS SDK. At the top of your Lambda, type const AWS equals require AWS SDK. You can use this AWS variable to create interfaces with AWS services. For instance, let's create a DynamoDB client by typing const DynamoDB equals new aws.dynamodb.document client. We'll also need to create a client for API Gateway to send messages back to all of our players. So type const API Gateway equals new aws.API Gateway Management API. This method's parameter is an object that contains any configurations you need. For our case, we'll need to specify our endpoint. Again, grab your WebSocket endpoint from your production stage API Gateway console page. Don't include the WSS. Using these clients, we can do things like add entries to our DynamoDB table or send messages back to our players through API Gateway. But before we do that, I need to quickly talk about another AWS service called IAM. IAM is AWS's security controls. Whenever an AWS service calls another AWS service, they use a seeker key called an IAM role to let AWS know they have permissions to make that call. When you created your join Lambda, an IAM role was automatically created. However, this IAM role doesn't currently have permissions to call other services like DynamoDB or API Gateway, so if we try to use these clients right now, it'll throw an error. So, let's quickly give our join Lambda's IAM role permissions to do that. Open the IAM console page and click Roles on the left side. You should have a role called Join Role. Open it and click Attach Policies. Check the box next to Administrator Access and click Attach Policy. Doing this gives your Lambda function the permissions to call any other AWS service. Typically, you should create a specific policy for each Lambda that only allows it to call the services and APIs you intend to use, but for a quick and dirty solution, giving it administrator access is fine. I'll go over IAM in more detail and talk about best practices in a future video. For now, back to implementing the join Lambda function. First, let's create a player object. Add the connection ID and a position. Next, we need to use the DynamoDB client we created to add this object to our players table. Call dynamodb.put. The parameters for this function are table name, which is players, and item, which is our player object. We want to make sure this call to DynamoDB completes before we end our Lambda, so let's add a .promise and add await to the front. If you don't know a lot about async, await, and promises in JavaScript, I highly recommend doing some research before making more Lambdas on your own. It's a super useful tool and can help cut down on the runtime of your Lambdas by a lot. Before we test again, return the player object back to the caller as a list instead of this test packet. Hit deploy and let's run our Unity game again to send another join packet to see if it successfully makes our entry in our players table. Good, we got the response we expected. Now let's open the DynamoDB console page, go to tables, select our players table, and check the items. Yep, there's our player we just added. For simplicity, we are only storing the position along with the connection ID, but we could add as much data as we need to our player object before we store it. There are a few more things we need to add to our output so that the client knows what to do with packets when they get them. First, I'm updating the comment at the top with what we'll be changing. I'm adding an action property with the value join and the joining player's connection ID. After this, we'll update our Unity game to spawn player objects for each player in the list, and we'll know which one belongs to the caller. Next, working through the to-dos, I'm going to be calling dynamodb.scan to get back all the entries in our players table. DynamoDB returns paginated results, meaning that if we want all the results, we need to keep calling scan in a loop, providing the next token value we got from the previous call until we no longer receive a next token value. Then we're updating our returned value to match what we said would be in the comment at the top. Add the action and connection ID properties as well as concatenating the players to our players list. Finally, we create an add player message to send to the rest of the clients. We call API gateway.postToConnection to send this message to all players in our table. Using promise.allSettled and await as I do here means that we'll send this message to all players at the same time instead of doing them one at a time. Also, if any of them fail due to a player closing their connection before receiving the message or something, we won't fail the entire function. Next, let's update our Unity game to parse the new join and add player packets we'll be receiving from the server. First, add join and add player to packet action if you haven't already. Next, we'll need to create the packet classes that are just C# versions of the JSON packets that we'll be receiving from the server. Create JoinPacketInc and AddPlayerPacketInc and add public properties that mirror what we'll be sending from the server. You'll need to make player and position classes as well. Then, in Websocket.cs, add cases for these two packet actions. We'll just be invoking events from our WebSocket that our game manager can listen to. So, create two new events called joinEvent and AddPlayerEvent and have their corresponding packets as the parameter. Call JSON_convert.deserialize object on the received message to turn the JSON into the C# packet classes you just made and invoke the events. We'll have our game manager subscribe to those events in the start function. When the join event is invoked, we'll have our game manager instantiate a player prefab for each player. I'm going to quickly make a player prefab in PlayerController. When the game manager instantiates the prefabs, I'll have it call a method to highlight the text if the connection ID matches the one we were sent by the join packet. I'll also have the game manager instantiate a player prefab when it receives an add player packet. Next, I'll be creating a move route in Lambda, so I'll make it so when we click on the screen, it sends a move packet with the X and Y coordinates. I'm going pretty quick here, but you can find the code for each step in the description below. We've just got to make two more Lambda functions and update our client to respond to those functions and we'll be done. Let's go back to the Lambda console page and create our last two functions. Call one move and the other disconnect. Both of these will be pretty close to our join Lambda, so let's copy paste that code over to our new functions. For move, just change the word add player to move and remove the body from the return. We'll also change the X and Y position to the values from the input body. Since we're using dynamodb.put here, it'll overwrite what's already in our DynamoDB table instead of updating it, but that's alright since the only thing we're updating is the only other value in the object. If you only want to update parts of the entry, you can use dynamodb.update instead. Documentation on how to use that method are available online. We can remove the body from the return since we don't need to send something different back to the caller of this function. They get the same move response that all other players get. For disconnect, we can remove the player object creation and replace dynamodb.put with dynamodb.delete, providing the connection ID is the key. Replace add player with remove player and remove the body from the return as well. It might be worth moving the delete item call above the scan call so that we don't try to send the removed player packet to the player that just disconnected as well. And since we have two new lambdas that need permissions to call DynamoDB and API Gateway, open up IAM again and slap that administrator access policy onto both roles as well. Finally, we need to make the routes for our two new Lambda functions in our API gateway. Open your API and type move into the new route key box and click the checkmark. This time, don't click the integration response button since we don't need the caller to get our returned response. For the disconnect route, just click the plus next to the special disconnect route and do the same thing. Again, no integration response. Don't forget to deploy your API after you make your changes to your routes. The only thing left is to update our client to parse the new move and remove player packets. Add the cases to the receive method in Websocket.cs and notify the new events. Have GameManager subscribe to those events and either move the player or remove them. And there we go. We created a browser-based online multiplayer game in under 20 minutes or so. That leaves plenty of time in a 48-hour game jam to make something interesting from this base. Let's rubber duck through the code one last time so we can truly understand what is happening at each step. A Unity project is built to WebGL. The project is using the .NET Standard 2.0 DLLs for the Newtonsoft library. During compilation, Unity will keep the light lambda class file necessary for Newtonsoft to work due to our link.xml file in the assets folder. A player opens the game in their web browser. The scene loads and the WebSocket runs its start function. This calls the WebSocket.init method in the Websocket.jslib file, which creates a new WebSocket connection to the API gateway endpoint specified in that file. API gateway establishes the connection with the player. If we had specified a lambda to run during the connect route, this is when it would do that. However, since there is no connect route specified, API gateway simply returns to the client that the connection is successful. The WebSocket connection in Websocket.jslib's onOpen callback is run, which sends a message to Unity to run the init method on the networking game object. The WebSocket's init method is run, which notifies a init event. GameManager is subscribed to that event, so it runs its init function, which creates a JoinPacketOut.cs class, which then serializes to a JSON object with Newtonsoft. It then calls Websocket.cs's send method, which in turn calls Websocket.jslib's WebSocket send method. This sends the JSON packet through the WebSocket to API Gateway. API Gateway receives a packet from one of its connections. It reads the action property of the packet and runs the corresponding join lambda function, passing the connection ID to it through event.requestContext.connectionID. The join lambda is invoked. It first creates clients for DynamoDB and API Gateway. Then it logs the contents of event to CloudWatch. It creates a player object using the connection ID passed from API Gateway and calls DynamoDB.scan on the players table. DynamoDB scans 1 megabyte worth of entries in the players table and sends them back to Lambda. If there are more than 1 megabyte worth of entries, it'll also include a token called last evaluated key in the response. Lambda continues to call DynamoDB.scan in a loop until the last evaluated key is not returned along with the items. All those items are stored to the players list. Lambda calls DynamoDB.put and waits for Dynamo to finish. Once DynamoDB has finished putting the entry into the players table, it replies, and Lambda moves on to create an AddPlayerPacket to send to all the existing connections. Lambda calls API Gateway's post-to-connection to send the AddPlayer message to all the connections it got from DynamoDB. Once all the calls have returned either successfully or unsuccessfully, Lambda returns a join packet that contains the full list of players back to the original caller. API Gateway receives this returned response and due to the join route having integration response enabled, passes that response back to the player. Websocket.jslib's onMessage callback is run, which sends a message to Unity to run the receive method on the networking game object. Websocket.cs's receive method is called with a JSON string. We use Newtonsoft's JSON-convert.deserialize object to deserialize the JSON object into the Packet.cs class, which contains a PacketAction enum. We switch the packet action, and since the packet action is join, we deserialize the JSON packet into a JoinPacketInc object and invoke join event. Since GameManager is subscribed to join event, its join method is called. For each player in the packet, GameManager instantiates a player prefab, sets its position to the given position, and adds it to a dictionary. Sometime later, the player clicks on the screen. GameManager's update function is constantly checking if the left mouse button has been clicked. On the frame that it is, it gets the mouse's world position and constructs a MovePacketOut object with that position. It then serializes this packet to a JSON object with Newtonsoft's JSON-convert.serialize object and calls WebSocket.send. This, once again, calls Websocket.jslib's WebSocket send method and sends the JSON packet through the WebSocket to API Gateway. This time, when API Gateway reads the action property as move, it invokes our move lambda function. Move is very similar to join, but instead of putting a new player object into DynamoDB, it overrides the existing entry with the given position. All the connected players are sent a move packet with the connection ID and position of the player that just moved. When the players receive the message, the GameManager's move method is invoked, which gets the player with the same connection ID from the dictionary and sets the dest property to the given position. The PlayerController's fixed update function translates the transform towards dest until it reaches it. The player closes their browser, which closes the WebSocket connection to API Gateway. API Gateway's special disconnect route is run, which invokes our disconnect lambda function. The lambda calls dynamodb.delete to remove the player entry and sends a remove player packet to all other connections. And finally, the players that are still connected have their GameManager's remove player method called, which removes the player from the dictionary and destroys the player game object. Wow, that was a lot to go through. Sorry for rushing through a lot of it, but I hope you were able to follow along. There are quite a few things that I had to leave out for time, such as having multiple game sessions and using AWS's step function service to do things like have turn timers or simultaneous turns. I'd like to go over those things in future videos, so if you're interested in that, do the thing. If anyone uses this design to make an online multiplayer game of your own, let me know. I'd love to play and see what you've made. Thanks for watching, and good luck making games of your own in the future.